Hey, welcome to episode 7 of the Raised Beaches podcast. I'm your host, Dr. Evan James Gowan, but you could call me Evan. I'm recording on June 11th, 2026, and in this episode, I'm going to be discussing about the fact that it's been 1 year since I've done my last episode, and I'm going to discuss about my new job at Kikaijima and the Japan Geoscience Union conference from 2026, the end of the Ocean Observation Initiative, and some papers. So if you are watching the video version of this podcast, one thing you'll notice is that if you look over on my left side, there's a shelf full of clams, giant clam shells. On my right, there's an aquarium, and it's got some tropical fish and some corals growing in it. And this is because I'm filming at the Kikai Institute for Coral Reef Sciences. So starting in April this year, I got a position as a researcher at this institute. And in a previous episode, I did film in this very classroom that I'm sitting in right now. So the kind of research that they do here is very close to what I am interested in, which is in particular the paleoclimate of the past 120,000 years, as well as the sea level changes in the past 120,000 years, because Kikaijima is a rapidly uplifting island, uplifting at a rate of about 2 millimeters per year. And as a result of this sustained uplift over the past 130,000 years or so, there are coral reef terraces that are preserved at very interesting time periods where we don't have much information on the what the sea level was for those periods of time. Especially interesting is that they have dated coral fossils here that date to about 65,000 years ago, which is the peak of the marine isotope stage 4 glaciation. So in terms of the last glacial cycle, which started about 115,000 years ago, marine isotope stage 4 was a long cold period, and in some places it was actually colder than the so-called last glacial maximum. The fact that there's coral reef terraces that are preserved from that time is very intriguing to me, and I am really hoping to investigate the cause of the terraces at that time in Kikaijima. So in terms of this podcast, the way I originally envisioned it was to have sort of a intro period where I talk about things that have just been going on recently, and then to have a deep dive where I investigate a topic in climate change or paleoclimate. And that took a long time to do. Each episode was taking quite a while for me to do the research, to do the deep dives. And to be honest, especially in the past year when I was doing a lot of English teaching and creating the classes for those for that teaching, it just was not possible for me to maintain that kind of format. And so in reviving this podcast, I'm hoping to maybe keep things more fresh and not have these deep dives so that I can produce more episodes. And I still hope that it's interesting and I can bring to light a lot of the recent research in paleoclimate and paleo sea level changes. And so the teaching I was doing last year, it was very interesting. Although as an English teacher, I was teaching science students, so I did do a lot of science in my classes, specifically earth sciences and climate science. So like I had a class about earthquakes and volcanoes, and I had another class on the environment and another class on climate change. I also had a lot of the students were nutrition students, so I created a course on global cuisine, which was not really related to climate or earth science, but that was still quite a lot of fun. And I was also working on a couple of papers, and I'm hoping to finish them up pretty soon. I'm really hoping to finish one up this week, actually. And that also was taking quite a bit of my time. So the podcast was just not a priority when I was doing that. And another exciting thing that I did last year, back in September, was the Sango Hakobune, or the Arc of Coral Reefs. So this was done to celebrate the 10-year anniversary of the Kikai Institute for Coral Reef Sciences, where I am right now. And we went on this schooner called the Mirai A. So Mirai A, when translated to English, means towards the future. And as a schooner, we were expected to actually pilot the boat and put up the sails, and unfortunately there was not a lot of wind, so we left from Kikaijima, and for one day we tried to use the sails, but we weren't really going anywhere, so we eventually had to give up on that and just use the engine. But yeah, I got to pilot the boat, which was pretty fun. And the Hakobune cruise, like, it had scientists that have been involved at this institute, of course, which included me, but it also included a lot of artists and filmmakers, and there were a lot of students on board, and there were local people who they're all musicians, so that basically gave a little bit of a flavor of different backgrounds on this cruise, and we all got along very well, and it was quite fun. And I was interested in some of the stops we went on. So we stopped in Yakushima, which is this large island of granite, basically, and we stopped in Kochi Prefecture. And there were the organizers were interested in looking at some coral reefs that they investigated many years ago and seeing how they were. But when I was there, I was interested in the Holocene terraces, which had been uplifted due to earthquakes, or possibly because there was a high stand in the sea level in the Holocene. There was also this island called Inujima, which means dog island, and this was more for the artists on board. So the Inujima, it used to be a granite quarry. So if you've ever been to Osaka, the granite that's used in the harbor in Osaka and for Osaka Castle actually come from this island called Inujima. So Inujima means dog island. There's a big statue of a dog on there, and there was a smelter on there. So they've really shaped the island for the artists, though, to try and revive the island. And so the granite there, it was absolutely beautiful, and I can understand why it was used as a building stone. And then at the end, we went to Osaka, and the goal was to go to the Osaka Expo. I was unable to attend because I had some teaching commitments, but most of the people went there, and the musicians performed there, and yeah, that was a once in a lifetime event, and so one of the highlights of 2025 for me. And I've made a blog for that if you are interested in the details. So my blog is at raisbeaches.net. So I have a day-by-day rundown of the events on the Hakobune cruise. And so a little bit more about my current job at the Kikai Institute for Coral Reef Sciences. So I first came to Kikaijima about 4 years ago, and they have a lot of programs here geared towards middle and high school students. And in the summer, they have a summer school, which is, they have like a junior course and an advanced course. The junior course is really just to introduce different kinds of science to young students, and so it goes over the course of a few days, and the students do a little bit of a project and make a poster, and it's quite a bit of fun. I taught it a couple of years ago, and of course I'll teach it again this year. Then there's the advanced course, which is geared towards, so I maybe a bit more background. So at the Institute, in partnership with the town of Kikai, they have a so-called Sango Ryugaku, which maybe could be translated to the coral boarding school. So students from different parts of Japan can apply for this program, and they come to Kikaijima, and during the week they go to high school, and during the weekend on Saturday they start to work on a scientific project, and this lasts over the course of 3 years. In addition to that, they have this Sango Juku, which can be translated to the Coral After School program. And so both of those groups of students will, during the advanced course in the summer, conduct their research activities, which will serve as the basis of their final paper. So over the course of 3 years, they slowly develop their skills as a scientist and work on a project that interests them, so that if they are interested in going into science, they will have a big leg up when they go into university. As a researcher at the Institute, I get to help out these students. And the past 2 months, so I started in April, and the past 2 months I've basically been introducing the first-year students in this Sango Ryugaku program to geology, which for me, I'm a modeler, so I had to look up the geology and harken back to my undergraduate days where I studied geology and tried to remember all the concepts of the sedimentary geology. And there's the added challenge that I have to teach in Japanese. So I've also been learning a lot of the terms in Japanese. And one interesting thing about a lot of these geological terms in Japanese is that they are basically very precise translations of the English word. So as an example, one of the things we were looking at in one of the sediments were these single-celled fossils, so it's called foraminifera. So they're really, really small, and you can really only see them in a microscope. And we were picking them out and looking at them. And so foraminifera, it's a Latin-based word, which means has holes. And the Japanese word was yuko-chu. And what does yuko mean? It means has holes. So they just took the word foraminifera and translated it using Chinese characters. So that was pretty interesting. There's not a high level of English skills in the students, so it's been a big challenge for me to improve my Japanese. So it's like going back to school for me as well. Okay, the next topic is the Japan Geoscience Union meeting. So this happened in the last week of May, and it was done in partnership with the American Geophysical Union. And as a result, the main language of the conference was English. And This also made it so that there were a lot more participants from other countries. So in typical Japan Geoscience Union or JPGU meetings, the language in a lot of the sessions is Japanese. So it kind of is hard for a non-Japanese speaker to really get much out of that. So most of the researchers at a typical meeting are from Japan, and this time there was more sessions with people from abroad, so it had a bit more variety. And I gave a presentation on the Monday of the conference, and it was called An Investigation of the Evolution of North American Ice Sheets Through the Last Glacial Cycle. So I'm working on a paper on this, and I hope to have it finished up in the next couple of months. So stay tuned about that. And I also helped some of the Ryugaku from our research program here at the Institute. So there was three high school students who made a poster and presented it on the Sunday of the conference. So that was interesting. I even got to meet the president of the JPGU, so that was pretty fun. And of course, there's a bunch of. I tried to fill up my week by watching presentations. So I'm just going to highlight some of the interesting presentations that I saw. So first, there's a presentation by John Chiang, and he was looking at how orbital forcing changes the seasons in the tropics. So if you think about the tropics, you don't really expect there to be seasons per se, because the angle of the sun to the ground doesn't change a whole lot through the year. So, but it does change. There is seasons in the tropics, and it's affected by eccentricity. So I talked about this in a previous podcast episode, that the eccentricity is how round the Earth's orbit is around the sun, and so it shifts around a bit so that sometimes the Earth is closer to the sun in the summer than in the winter, or vice versa, and that actually has an impact on the sea surface temperatures in the tropics over time. So it was interesting to learn about that. The next presentation was by Nodoka Kuramoto, and they were looking at a speleothem record in Shiga, which is in central Japan. So a speleothem is a cave rock, so it basically is made with limestone that precipitates from drip water in a cave, so stalagmites, for instance. And over time, you get growth, and you can get very precise ages using uranium thorium dating. So it's kind of the gold standard for getting paleoclimate records. And unfortunately, Japan doesn't have a whole lot of these records yet. Just in the past 10 years, they've started to collect them. And this particular record is very long, and it has a strong correlation with the also high-resolution Lake Suigetsu lake core record. So the next presentation I want to highlight is by Sachio Nakagawa. So she was doing some climate modeling of the Pliocene. So Pliocene was a period of time between about 5 and 2.5 million years ago. And that was a time period where the Earth was warmer than it is now, but the configuration of the continents was roughly the same, and carbon dioxide was higher. Well, maybe not as high as right now, but higher than what has been in general in the past 2.5 million years. So it's looked upon as being an analog for future warming. So what she did was to investigate the relative rules of paleogeography changes and carbon dioxide. The thing about the Pliocene is that it was before the northern hemisphere was heavily glaciated. So there's areas where the glaciers have sort of scraped away the sediments, and back in the Pliocene, those areas like the Barents Sea were actually land rather than ocean. So the results of her model suggest that the rule of the paleogeography change is comparable to the rule of carbon dioxide in the warming during the Pliocene. So that was very interesting. All right, the next presentation that I wanted to highlight was by Hokuto Sugiyama, and he was working on doing some climate modeling of the last glacial maximum about 20,000 years ago in Okinawa. So Okinawa is actually southern Japan. I think many people probably know where it is. He was comparing a bunch of climate models and see if they can reproduce some of the proxy records that they have from Okinawa. What he found was that the models are able to reproduce the winter cooling that was observed in Okinawa, but not the summer cooling. So he proposed that it was due to improper vegetation modeling. Okay, the next presentation that I want to highlight was by Masanobu Yamamoto, and he was looking at changes in the tropical monsoon in the Indian Ocean during the mid-Pleistocene transition, which happened about 1 million years ago. So Yamamoto is perhaps best known for creating a very long record of carbon dioxide changes from leaf wax proxies in the Bay of Bengal. And this study was using those same cores, I believe, and it showed that prior to this mid-Pleistocene transition, which was a transition between glacial cycles that were about 40,000 years to glacial cycles that were about 100,000 years, and he found that the monsoon changes prior to this mid-Pleistocene transition were not directly connected to the ice volume changes, but after the mid-Pleistocene transition, it tended that there was more influence from the northern hemisphere glaciation. So prior to the mid-Pleistocene transition, there was the Indian monsoon had a larger competition between insulation changes in the northern and southern hemisphere. So that was pretty interesting. Another presentation was by Christo Buizert, and he provided an overview of how AMOC, the Atlantic Meridional Overturning Circulation, affects ocean heat content. And he's looking at it in a very broad perspective, like when the AMOC is strong, where does the ocean gain heat and lose heat? And when it's weak, where does it gain heat and lose heat? And different ocean basins will gain heat or lose heat depending on the strength of the AMOC. And one thing he noted is that the South Atlantic and the Pacific will always gain heat from the sun, and the North Atlantic and the Southern Ocean will always lose heat. But, of course, the Northern Atlantic is highly variable depending on the strength of the AMOC. And when the AMOC is weak, it will cause an overall gain in ocean heat content, and that's because the surface of the ocean is not getting subducted down into the deep ocean in the Atlantic, so the surface can warm up. And finally, there was a large contingent of session of people who had come to the conference to present on ice sheet basal conditions, and I've done some work on ice sheet basal conditions, so it was interesting to meet these scientists who most of them were based out of the United States, and so they had come to the JPGU conference because of the joint AGU meeting along with it. And one talk was by Atsuhiro Muto, and he was using seismic refraction to determine the conditions at the base of the Thwaites Glacier. So if you know about seismic reflection, there's a difference in the nature of the reflection of seismic waves in a solid medium, depending on the characteristics of the medium it goes through. So, the base of a glacier, you can have the glacier sitting on bare rock, for instance, or you can have the glacier sitting on unconsolidated sediments, or it can be floating on water, for instance. There could be a layer of water between the glacier and the ground that's underneath the glacier. And the seismic reflection or refraction signal will change depending on what sort of conditions are at the base. So, and this is important because the basal conditions of the ice sheet will affect how quickly the ice sheet will slide. So the Thwaites Glacier is being monitored a lot because if it completely retreated, it would cause a lot of sea level rise, and it's particularly vulnerable to retreat because of its position where the base of the ice sheet, or the base of the glacier, is well below sea level. So this glacier is probably one of the best known in the world, and it's in Antarctica, of course. Yeah, it's retreating right now, and so a lot of glaciologists, their activities are focused on trying to figure out how stable this glacier is. The second presentation I want to highlight from the basal condition sessions was by Sridhar Krishnan, and he won the 2024 Seligman Crystal from the International Glaciological Society, and this is basically the highest honor of the Glaciological Society for contributions to glaciology. And he's done a lot of work using seismic data to infer the conditions of ice sheets. And so this talk was more of a look back, and it was very sentimental. So it was very enjoyable to watch his talk. And the third presentation I want to highlight was by Olga Sergienko, and she was looking at the physics of ice in Greenland over areas that the bed topography is very variable. And so for the physics of ice, so ice is a very complicated solid in some ways. It's sort of like halfway between a solid and a liquid. And we usually, to properly model ice flow, you need to use what is known as the Navier-Stokes equation. And this is a very complicated equation, and it's very computationally intensive to solve. So for modeling ice sheets, we typically use an approximation so that it simplifies that formula. However, in her presentation, she demonstrated that the ice flow calculated using this approximation is not particularly accurate in these areas where the base of the ice sheet is highly variable. And yeah, when I did my postdoc in Sweden like 10 years ago, we were also investigating this problem, that in places where the base of the ice sheet is not flat. This approximation that we use, which is known as the shallow ice approximation, doesn't really work so well with the paleo ice sheet modeling that I do. We have to use this approximation. Like, we don't really have a choice. We can't use the full equations. It just is not feasible to calculate the ice sheet over thousands of years without using this approximation. So the main message is that for 100 years in the future, you really need to use the proper equation and not the approximation. Otherwise, you're not properly capturing the dynamics of the flowing ice. So yeah, I had a great time at the Japan Geoscience Union. I always have a great time there. It's a great conference. Always nice to meet all my colleagues and to get lots of ideas on what direction my research should go. And I look forward to it next year. Okay, the next topic I wanted to talk a little bit about was the end of the Ocean Observation Initiative, and this sort of was announced last week. So I'm sure most scientists are aware of the fact that the political environment in the United States is not very friendly towards sciences, and especially earth sciences, and the National Science Foundation, which provides funding for much of the earth science that is done in the United States, is basically stopping the funding of earth science in general. And one of those things is the Ocean Observation Initiative, which is basically a series of undersea cables that stretch out into the deep ocean, and they have sensors I don't know how far apart they are, but they have sensors that do lots of different kinds of measurements. And so I don't know a whole lot about it, but I remember during my master's degree in Victoria in Canada that they had this sort of measurement system. One of them was called the Venus Project, and it connected Victoria to Vancouver with this undersea cable, and they were measuring the properties of the Salish Sea. And the second one, which they were in the process of deploying it while I was doing my master's degree, the Neptune Project, and it basically stretched out from Vancouver Island to the subduction zone that was off the coast. The primary reason to do this is that they have seismometers along these networks, and it provides an early warning if there is a major earthquake so that people can escape the upcoming tsunami. So these undersea observation networks, the United States, of course, has done this with the Ocean Observation Initiative, and Japan has their own networks as well. And they're not just seismometers; they're also measuring the properties of the ocean and monitoring animals and creatures on the seafloor. One of the things is that the United States had set it up in the Atlantic Ocean, and it was monitoring the Atlantic meridional overturning circulation. And of course, if the AMOC, as it's called, collapses, it will basically mean that the climate in places like Northern Europe, Iceland, Greenland will become a lot colder than it is now. This is, and of course, if the AMOC shuts down, it affects the global wind patterns as well. So it'll change, like the monsoon in Asia, for instance. So the U.S. set up the instruments to measure changes in the AMOC, and now they're just going to rip it all out. So we're going to lose our capability to measure changes in the AMOC directly, and so we'll be basically forced to use satellite measurements, for instance, which is not quite as accurate. So it's really sad that they're just ripping it up because it costs a lot of money to put things out. And the thing is, all around the world is the same thing. All of these very major earth science projects are very costly, and governments around the world are basically saying, we can't do this right now. We don't have the resources to do it. So a lot of the big research projects are just not happening anymore. So the U.S. is cutting back, and it's a real shame because the U.S. was the major funder for a lot of these projects. They also shut down the JOIDES resolution, which did the ocean drilling projects. That was shut down 2 years ago. So, for a lot of the work that I do, I rely on these measurements that are made in these large projects, and to collect data like this, it's a huge logistical challenge, and it's quite expensive. So it makes it an easy target, but the problem is that without this data, we can't move our science forward. So I really hope this gets reversed before they rip up everything. Finally, I'm going to discuss some papers. I've got 2 papers this time. I'm co-author on both of them, so I thought I would highlight some of the stuff that I've been working on the past couple of years. The first is a paper that's led by Carla Rubio Sandoval, and it's titled Holocene Relative Sea Level Changes from the Atlantic Coasts of South America. So this was a big compilation of sea level data from a region that stretches between Brazil and southern Argentina. There's even some Chile data from Tierra del Fuego. And she did this massive effort to compile 1,100 sea level proxies from this coastal region. Most of the data cover the Holocene, but she also put in some data from the deglacial period that I personally requested, because for me, that is the most important data to constrain the ice sheet models. So what's interesting about the coast of South America is that there's a Holocene high stand. So the sea level in the middle of the Holocene was 2 to 4 meters higher than it is now across most of the coast of eastern South America. And this is related to glacial isostatic adjustment. So in the northern hemisphere, you had ice sheets covering Canada and Europe, and those ice sheets melted, and they completed their melting about 6,500 years ago. And not so coincidentally, the Holocene high stand in South America is at about the same time, and the sea level has been slowly falling ever since then. And this is a consequence of the rebound in the northern hemisphere, and also some changes to the Earth's axis of rotation. So one factor is that slowly, as the ocean floor in the Atlantic starts to sink, as the land in North America and Europe rises up, causes there to be more volume of water that can be held in the northern Atlantic Ocean. So that causes some of the water to move back to the southern hemisphere. And there's also changes to the Earth's axis rotation, which also causes water to move to the northern hemisphere. So these two things are basically causing a slow decline in sea level in South America. And using Carla's big compilation, we were able to really provide a solid estimate of when the highest stand was in various parts of eastern South America. And it also showed that my ice sheet reconstruction needs some work. The calculated sea level using my reconstruction did not fit this high stand that's observed there. So I'm hoping that the ice sheet reconstruction I'm working on now will fix some of that problem. The second paper is by Howe et al., and it was titled Model Seasonal and Proxy Spatial Biases Revealed by Assimilated Mid-Holocene Seasonal Temperatures. So that's a bit of a mouthful, even for me. And this was a modeling study investigating what is known as the Holocene temperature conundrum. So there are estimates of the global average temperature from proxies for the Holocene, and they mostly suggest that in the mid-Holocene there was a period of time where temperatures got kind of a bit warmer than they were like 150 years ago. So there's a peak in warming and then a gradual cooling after that. But the climate models, they all suggest that there's just been a gradual warming throughout the Holocene, and this is known as the temperature conundrum, the Holocene temperature conundrum. And so Howe et al., which included me, they used a method called paleoclimate data assimilation, and this is not the Borg or anything. This basically what it is you take the results of a climate model and you take those proxy-based estimates of temperature and you statistically combine those two things to adjust the climate pattern in these models using machine learning. So this is a machine learning technique. All climate models have a particular bias, and by using the data, you can sort of nudge it so that it accounts for that bias and produce a more realistic distribution of temperature. And the result of this, much of the focus of this paper is on Eurasia, and that's because in Europe, there's a lot of data. And that was the main problem, is that probably the source of this conundrum is that Europe has a large concentration of data, and Europe definitely had a warm period in the middle of the Holocene, and it cannot be determined precisely in other parts of the world that there was this warm period because there's simply not enough data. And one of the focuses of this paper is looking at Asia, and there's places like in Central Asia and in Siberia where there's simply not very much paleoclimate data, and the result of the assimilation shows there's very large uncertainties in those regions to estimate the Holocene temperature. And looking at a more global perspective, there are large parts of the world where there's no paleoclimate data. For instance, the Southern Pacific Ocean. There's no proxy data from there for the Holocene. It's just ocean. It's deep ocean. So one of the problems with the deep ocean is that we can use foraminifera to deduce the paleoclimate, but in the deep ocean, if the water is too deep, the foraminifera tests the carbonate shell-like things that these foraminiferas create. They simply dissolve in the water at depths below 4,000 meters. So not only is it difficult to get to the Southern Ocean to collect samples, if the ocean water is too deep, you just can't get the samples that you would need to deduce the paleoclimate. And so as a result, the temperatures in the Holocene optimum period, where some of the proxies say it was warmer than the pre-industrial period, maybe that cannot be used as a basis for estimating the global average temperature, because the data are biased, and the models are also biased. They have their own biases. So many models have a high latitude bias. So that's just a reality that we have to deal with, that we can't know everything. So the bottom line is we need to collect more data in places where we don't have data, and we also need to improve the models. So it's a great message. Lots of work to do. So always need to improve models and always need to collect more data. All right, that's the end of episode 7 of the Raised Beaches podcast. And if you're watching the video version, you probably noticed that the lighting has changed throughout this recording as the sun set. And anyway, I am hoping to do this podcast a little bit more frequently, trying to be a bit more flexible about the topics that I discuss, and hope that you enjoyed this. So see you next time. Thank you for listening to the Raised Beaches podcast. If you enjoyed this, please follow my social media accounts, where I post more information on the paleoclimate sciences. I am on Mastodon with the username @DrEvanGowan@FetiScience.org. On Bluesky, my username is @evangowan.bsky.social. On LinkedIn, my username is Evan James Gowan. I hope you tune in next time. Thank you.